This is Dr. Holt. In this video I want to solve a problem where I have an artificial satellite. It's going to be circling the Earth. It completes each orbit in 138 minutes. We want to find out what is the value of g at the location of the satellite. The mass of the Earth is given as 5.98 times 10 to the 24th. The universal gravitational constant here is given as 6.67259 times 10 to the minus 11th. So what I have here is I have a satellite is circling around the mass of the Earth here. So we know it has a velocity, so I'm going to go ahead and give it a velocity vector coming off like this. Try to draw that close as I can as tangent. Now if we draw a force diagram or free body diagram of this object here, what we would have would be we'd have the gravitational force coming down here, Fg. And now since it's in an orbit, we would have mass times acceleration coming down. So that pretty much there's our free body diagram. But off to the side here, I'm going to set that equal to mass times centrifugal acceleration. So if I sum my forces in the y and set that equal to mass times acceleration, and I'm going to let anything that goes down to be positive, then all I would have would be force of gravity is equal to mass times centrifugal acceleration. Alright, so now I'm going to scroll down here. I'm going to go ahead and set up this force of gravity. We know force of gravity, by definition, is going to be the value of g, the universal gravitational constant, times big M, which is the mass of the Earth, times little m, and we'll call it little ms, mass of the satellite, over r squared, or you can call it d, whatever you want to do. R squared means that's going to be the distance from, I'll just draw this, from the center here out to this distance here. Again, you can label that as r, or you can label it as d. So that's going to be the force right here that's trying to pull this object down to into the Earth, and that, and that's the same force this satellite's trying to pull Earth toward it. Alright, I'm going to set that equal to mass times centrifugal acceleration. Now the mass here is going to be the mass of the satellite. And we know the centrifugal acceleration is velocity squared divided by r. Alright, at this point you can simplify your equation. The mass of the satellites, that's meaningless, they're gone. R here is gone. This becomes just r. Alright, now the problem is here you do not have the velocity. However, you do have the period, and the period is given as 138. We can go back and we know that velocity times some time interval is equal to some distance here. And the distance is going to be the circumference of this. The circumference equation is nothing more than 2 pi times the radius. Alright, so we're going to say that the velocity then is going to be nothing more than 2 pi times the radius times t. But now we know t is 138. So I take t, I'm going to set that equal to 138 minutes. We're going to go ahead and convert that to seconds. We need to get that into seconds. So that's 60 seconds over 1 minute. Minutes cancel out, minutes cancel out. We'll run that calculation right there. Whoops, grab my calculator. So I drop stuff. 138 times 60 gives me 8,280 seconds. So t is equal to 8,280 seconds. Alright, so now we put that back into here, and I can say my velocity is going to be nothing more than 2 pi times my radius over 8,280 seconds. Alright, we're going to go ahead and substitute back in. That gives me g times big M, being the mass of the Earth, over r is equal to 2 pi times r over 8,280. We're going to go ahead and square that because that's all I got left on that side here. Okay, scroll down here a little bit, give myself some more room. And that's going to leave me G times big M over R is equal to, now we're going to square everything in here. That's going to give me 4 pi squared R squared over 8,280 squared. I'm going to go ahead and bring the R up to here. So I'll cancel that out here, or bring it up to the other side, whatever you want to call it. I'm going to go ahead and erase this 2, and that becomes a 3. So now R has gone to the 3rd power. I'll make that black so you can see it. Alright, now we're going to be ready. We're going to go ahead and isolate R cubed first. So I can call that G times M times 8280 squared over 4 pi squared is equal to R cubed. Alright, so now can we not say that R is going to equal to the cubed root of G times the mass of the Earth times 8280 squared all over, and let me change that because all that's inside that's cubed root. Of 4 pi squared. Alright, so now let's go ahead and put in the values. Okay, so R is going to equal to the cubed root of, and we're going to, usually you do 6.67 times 10 to the minus 11th. On this problem, they give you a different value for the universal gravitational constant of 6.67259. Okay, times the mass of the Earth, which is what, 5.98 times 10 to the 24th. Let me just verify that's right. That's what I remember anyway. That's correct. Okay, times 8,280 squared divided by, in parentheses, 4 times pi squared. And then we're going to take the cubed root of that. So let's try that with a calculator. We will take 6.67259 times 10 to the minus 11th times 5.98 times 10 to the 24th. Oops, let's get rid of that real quick. Times 8,280 squared divided by, in parentheses, make this a double parentheses here, 4 times second pi squared. Okay, we're going to take that all to the 1/3 power. That'll give us a value of R is 8,000, sorry, not 8,000, 88,49095 meters. Alright, so that's how far the satellite is from the center of the Earth. And now the question asks us, what is the value of G? Well, to find the value of G, we know, scroll down a little bit, we know that G is going to equal to the universal gravitational constant times the mass of the Earth divided by R squared. So to find G, put G into here. We have 6.67259 times 10 to the minus 11th times the mass of the Earth, 5.98 times 10 to the 24th. We will divide it by the radius squared, which is going to be the 8849095 squared. Okay, I'll go ahead and run that value of G and see what we get. So I'll take 6.67259 times 10 to the negative 11th times 5.98 times 10 to the 24th. We'll divide that by what we got for the radius squared. And let me see if I can find that real quick. Yeah, there it is. I don't know why it keeps coming up, sorry. So that's going to give me a G value of 5.0956. And that would be meters per second squared. And that would be the G value. So that's how you set up a problem like this. Again, work through it a few times. It's not as bad maybe as what it seems. Pretty much just have to be kind of methodical. The most important thing really is to recognize that you can get velocity in terms of the distance the object, the satellite, is from the center. That's what the key of this problem is. Alright, best of luck.